So welcome everyone to today's CDAC webinar. It's my great pleasure to introduce our speaker, Nir Goldman. We've been trying to get him on board for a talk for several years now, so finally we're going to hear from him. Nir is a theoretical chemist who's made many contributions to quantum simulations and reactive force fields with applications to astrobiology, to laser-driven dynamic compression experiments, and on the programmatic side to corrosion on metals, metal oxides, and aging and degradation of polymers. Nir has a bachelor's degree from Yale and a PhD from Berkeley. He was a postdoc after his time at Berkeley and became a member of the staff in 2006. He's also an adjunct associate professor of chemical engineering, and he's currently a deputy group leader in the non-equilibrium theory, materials dynamics, and kinetics group of the material science division at Livermore. Nir has won a number of awards, including fellowship in the American Physical Society, and he's won a number of awards from the Physical and Life Sciences Directorate at Livermore. In the last few years, he's turned his attention to machine learning and the applications to reactions of materials in extreme environments, which he's going to tell us about today. So welcome, Nir.
All right. Thank you, Russ. Thank you, everyone, for attending. It's very fun to be here. Yes, today I'm going to talk about machine learning driven simulations of reactive materials. I decided to focus today on high pressure, high temperature conditions for this audience. And really, what I mean here are machine learning approaches for atomic level simulations like molecular dynamics. So I'll give some background on that. The idea here is to start with sort of very difficult computationally intensive approaches like, density functional theory, things like that, and to then use machine learning as surrogates, or et cetera. Okay, first for the acknowledgement. So I picked a smattering of topics to discuss, and this has involved a lot of people. I'd like to point out Becky Lindsay. She was a postdoc that worked with me and then moved on to the University of Michigan. Hui Pham, Larry Freed, Jared Stimac, Eric Cheng, Gautam Strosio, and Quangnam Lim. They're all part of the Chimes development group. Chimes is a model I'll talk about soon. Ricardo Dettori actually is now at the University of Cagliari. I'll also talk about some semi-empirical quantum simulations. University of Bremen, Becky again, Hui, and Matt Kroonblad from our lab. Okay, so this is sort of an overview of how machine learning driven simulations can be useful kind of on the atomic level. And really what we're interested in here are materials that are reactive under various thermodynamic conditions. And the problem is that one problem that we want to address is that the development of new materials with tailored properties can be a combinatorial problem. So there are lots of different permutations of initial conditions, reactive conditions, etc. So what I have here in my cartoon is that, on the left is sort of how things tend to proceed, which is a new material is developed. So you have some concept, synthesized, maybe you make something out of it and then you test. And this is very hard to direct. And so in general, it's directed in an Edisonian way, sort of by trial and error. We frequently talk with experimentalists who want some kind of help from people like me who do calculations. And what they really hope for is something that is plug and play. So they can tell me what they want, they can give me a set of properties, and then I can help narrow down what it is that they have to do to synthesize that material or, to get at least things in the ballpark for what they might want. So they want something that can be readily used that can give very quick answers. And that is really the problem here, because what really happens for most of us who do these kind of machine learning driven molecular dynamics simulations is something very labor intensive. So we might start with quantum simulations. So for the non-condensed matter physicists and non-chemists, that would mean density functional theory. calculations. So we treat the electrons quantum mechanically. Those are very computationally intensive. You generate a data set, you maybe pick some kind of machine learning molecular dynamics model, you train, you validate, you have some kind of loop that you iterate on until things are done, and you have a final model. This kind of approach is what most people do. It's what I do frequently myself, but it's very time intensive. It can take months to years to develop a good model, and you need a high degree of expertise to really get something that you can find believable that will be useful to an experimentalist. Whereas what they really want is something very fast. So one of the issues I've spent some time thinking about over the last few years is this idea of how can we avoid reinventing the wheel? In this case, we're constantly reinventing the wheel to get these kinds of models by following this kind of labor-intensive iterative process. Are there ways in which we could speed this up or maybe even create off-the-shelf models that would be more applicable right here in terms of closing the loop for what experimentalists want? Okay, given all that, I decided